Major studio releases once hit shelves every 2 to 3 years. Today, the timeline for a standard AAA sequel stretches up to a full decade. This expanded timeline carries an immediate financial penalty. For a top-tier studio aiming to compete in the current market, $100 million is now the baseline entry fee. When internal Sony documents leaked during a recent FTC trial, the actual figures bled through poorly placed blackout markers. Horizon Forbidden West, a flagship PlayStation release, carried a final price tag of $212 million, requiring over 300 employees. The Last of Us Part 2 demanded 70 months of production and $220 million. Spider-Man 2 pushed that figure up to $315 million. Now, industry projections place the upcoming Grand Theft Auto 6 somewhere between $1 and $1.5 billion. For years, studios operated by doubling their budgets and extending their production windows to match the power of each new console generation. That mathematical model has reached its breaking point. In software development, time directly translates to payroll. Every additional month a project remains in production adds tens of millions of dollars to the final ledger. To manage these sprawling titles, studios have scaled their workforces entirely out of single office buildings. What used to be a local team of 40 has become a synchronized global network of over 1,000 specialized developers. Expanding a timeline from 3 years to 6 creates compounding costs. Teams face continuous scope creep, mandatory engine upgrades, and years of accumulated rework to ensure the game doesn't look visually outdated by the time it finally ships. This scale is not driven by creative ambition alone. It is a direct symptom of the extreme technical friction required to achieve modern photorealism. The push for perfectly realistic environments means every visual element requires an immense amount of data. This flowchart illustrates photogrammetry. Developers take hundreds of photographs of physical objects to build an accurate digital base. Moving to the cleanup phase, the raw scan creates a chaotic, high-density mesh. This output is far too disorganized to drop directly into a live game engine. This creates a massive manual labor trap. Artists must isolate the asset, retopologize the wireframe, optimize the shaders, and repair textures by hand, a process taking hours for a single object. While film production or museum archiving can comfortably process this dense point cloud data, like the rendering of the human subject shown here, video games must calculate and render these objects interactively, 60 times per second. When an open-world map requires millions of individual rocks, trees, and props, the mandate for photorealism grinds production to a halt. Every single surface demands manual human validation. Creating these assets is the first hurdle. The second is forcing consumer hardware to run them. Epic Games attempted to solve the asset density problem with Unreal Engine 5's Nanite system. Instead of building multiple manual versions, Nanite virtualizes the geometry, dynamically shifting the polygon count based on camera proximity. While it saves artists time, it congests the hardware. Running Nanite at 4K resolution requires the graphics card to map millions of microclusters into a visibility buffer, quickly maxing out VRAM capacity. Compounding this is Lumen, a lighting system that calculates global illumination and bounces light rays in real time, eliminating the need to pre-bake shadows, but placing heavier demands on the GPU. Consoles handle this weight because their hardware is identical across all units, but pushing these advanced rendering features onto the PC platform triggers the modern shader compilation epidemic. Because every PC has a different combination of components, developers cannot ship pre-compiled code. When a visual effect appears, the CPU translates code to the GPU on the fly. The pipeline stalls, and the game physically freezes. To mitigate this stutter, development teams spend months building pipeline state object caches, forcing players to pre-compile the entire game in the main menu before taking a single step. Beneath the asset creation and hardware rendering lies the deepest bottleneck, the aging code architecture of the game engines themselves. Top-tier studios historically built and maintained their own bespoke engines. This kept them independent and allowed them to optimize their code directly for specific console hardware. CD Projekt Red followed this path with their proprietary Red engine. Because game mechanics shifted drastically between titles, engineers had to rewrite foundational components entirely from scratch for every release, steadily compounding their technical debt. This isolation creates a logistical nightmare for staffing when a studio scales up to 1,000 people. New engineers face a 6 to 9 month onboarding period just to learn how to operate tools that don't exist anywhere else in the industry. Facing these impossible timelines, the industry is pivoting towards standardized commercial platforms. CD Projekt Red signed a 15-year partnership with Epic Games, abandoning Red Engine entirely to migrate their future titles to Unreal Engine 5. Development studios are surrendering total technological independence. The internal cost of maintaining a foundational engine has simply eclipsed the value of using it. With budgets maxed out and hardware pushed to its absolute limits, the industry is searching for a way to stop the next generation of games from requiring 15 years to finish. The solution is pipeline acceleration. Studios are prioritizing faster iteration and efficient workflows over brute-forcing visual fidelity. This is where artificial intelligence enters modern production, but its actual application is highly pragmatic. Machine learning is not generating the core creative assets, nor is it writing the game's story. Instead, these tools automate tedious technical polish. They instantly validate geometry and fix UV layouts in seconds, replacing days of human labor. By integrating these automated toolchains directly into standardized platforms like Unreal Engine 5, developers can finally maintain a scalable workflow across a 1,000-person team. Studios are not trying to return to 2-year development cycles. Their objective is to compress the repetitive middle phases of production, keeping the overall timeline from expanding any further. The future of blockbuster game development requires giving up absolute technical control. Relying on standardized engines and automated assistants is the only way these massive interactive worlds can actually be finished and delivered to players.